After finding out inductance of a transmission line, let us try to find out capacitance of the line. So the formula for capacitance is charge divided by voltage difference due to the charge. So to find out capacitance on a line, we will consider the, let's say conductor is cylindrical. We will consider that to this conductor we have a charge Q per unit length, and due to this charge we will try to find out voltage difference between the two conductors. Okay, due to this charge we will try to find out the voltage difference, and for calculating C we will divide the voltage difference, we will divide the charge Q by the voltage difference. And how would we calculate the voltage difference? Then we will have charge Q, then we will find out the electric field using Gauss law and with the formula E is equal to minus dV by dr, or V12 is nothing but integration of electric field dr from 1 to 2. With this formula we will find out the voltage difference. So from charge we will have electric field using Gauss law. What is Gauss law? The total surface integration of electric flux is nothing but charge enclosed. With this formula we will find out the electric field. D and E are related as D is equal to epsilon into E. So with this formula we will find out the electric field, and after electric field we will try to find out the voltage difference. Let's say we have a cylindrical conductor, and this cylindrical conductor is carrying a charge Q per unit length. Okay, let's say this is a section of long conductor. Let's say the length is L, and it is carrying charge Q per unit length. Now due to this conductor and the charge on the conductor, let us try to find out difference between the potential of 2 points. Let's say this is D1 and this is D2. Okay, or before that let us try to find out electric field at any distance x from the axis of the cylinder. Let's say try to find out electric field at this point. Okay, so passing through this point we will draw a coaxial cylinder. We will draw a coaxial cylinder. Such that on the each part of surface of this coaxial cylinder E will be same, because each part of this coaxial cylinder will be at same distance x from the axis of the cylindrical wire. Okay, now let us try to apply the Gauss law. D dot ds integration will be charged enclosed. Okay, so on each surface D will be constant, or let us represent D as epsilon into E dot ds will be charged enclosed, or E dot ds will be charge enclosed divided by epsilon. Epsilon will be the permittivity of the medium. Since E will be same throughout the surface, integration of ds will be epsilon. And what will be ds? ds will be total surface area of the cylinder, and Q is the total charge enclosed. Total charge enclosed by the surface area, by the surface. Okay, so what is the total surface area? Total surface area of the cylinder will be 2 pi, total surface area will be 2 pi r into length L. So E into 2 pi, the radius is x and the length is L. This will be equal to total charge enclosed. Now Q is the charge per unit length. So the total charge from here to here will be charge per unit length into the length. Q into L divided by epsilon. So L and L will be cancelled. So E will be Q divided by 2 pi x epsilon volt per meter. Okay. So at any distance x, electric field can be given by this formula. Now let us try to find out the potential difference between, let's say this point is T1, this point is T2. Okay. Obviously the direction of electric field will be outside the surface. So we will apply the formula. dV by dx is nothing but, or electric field is nothing but the rate of decrease of potential difference with distance. So this will be equal to Q divided by 2 pi epsilon x. So V will be nothing but or the change in electric field will be minus Q divided by 2 pi epsilon x dx. Sorry, Q divided by 2 pi epsilon x dx. Let's say you are moving from point 1 to point 2. So what will be change in potential? Let's say here you have potential V2, here you have potential V1. So the change in potential while moving from 1 to 2, this will be V2 minus V1 is equal to minus, you are moving from point 1 to point 2. So first electric field of point 1, then 2. Or if you will take this minus to left hand side, what will you, we will have V1 minus V2 will be 1 to 2 Q divided by 2 pi epsilon 1 by x dx, 1 by x dx. And what is V1 minus V2? V1 minus V2 can be written as V12, the potential difference V12. Q divided by 2 pi epsilon, this will give you ln x from 1 to 2. Okay, it means ln distance of the position 2 minus distance of position 1. So V12 is Q divided by 2 pi epsilon ln position of point 2. So this will be, let's say this distance is d2. This will be d2 divided by d1. Sorry, here we will have ln. So this is the formula to find out potential difference between 2 points due to a current carrying conductor having charge Q per unit length. Okay, so we will apply this formula to find out capacitance between the capacitance of a conductor. Let's first assume two-wire system. Let's say this is wire X, this is wire Y. First for incoming current and other for returning current. So if this conductor will carry a current, a charge Q per unit length, obviously the another conductor will carry minus Q per unit length. Okay, let's say these are the two conductors X and Y. Okay, so these two conductors will behave as two plates of capacitor having charge q and minus q. Okay, so the capacitance will be q divided by voltage difference between the two conductors. So all we have to do is to find out the voltage difference between the two conductors, and for finding out voltage difference we will apply this formula. Let's say we have to find out voltage difference between x and y. This is voltage difference between 2 points due to a current carrying conductor. Okay, here we have two current carrying conductors, so we will find out the voltage difference between the two carrying conductors separately. So let us first try to find out voltage difference between x and y, Vxy, due to this first conductor. So what will be Vxy according to this formula? The charge per unit length is q divided by 2 epsilon ln distance of this conductor from this conductor only. Okay, first according to this formula, first write down the distances. Q divided by 2 epsilon ln d2. What is represented by 2? 2 is for y here, so here we will represent dy divided by dx. Okay, now in the calculation of capacitance we will consider that this conductor is an ideal conductor and the internal resistance of conductor is 0. Okay, and if this is a perfect conductor, the potential inside a perfect conductor, electric field is 0. Okay, if inside electric field is 0, E is equal to minus dV by dx. If inside a conductor electric field is 0, the rate of change of potential will be 0. So inside a perfect conductor, let's say this is a conducting surface. So inside this surface, at each point as well as on the surface, the potential will be same at each point. Okay, so if you are interested to find out the potential difference or the potential of this conductor, potential inside this conductor will be equal to the potential at surface. Okay, so if we take the potential at surface, Vx as this will be nothing but Vx minus Vy. Okay, so potential of conductor X inside this conductor can be taken as the potential of the surface only, and for surface dx can be taken as the radius of this conductor. Okay, so I just want to explain why at the place of dx we can take the radius of the first conductor. Okay, so we will have 2 pi epsilon ln, what is dy? Dy is the distance between these two conductors. Let us take this distance as d divided by radius of the conductor. So this is the potential difference between conductor X and Y due to the charge on conductor X only. Okay, now let us try to find out the same potential difference due to charge on Y conductor. We again have to find out Vxy, and we will add these two potential differences. But at the place of Vxy, let us first write the expression of Vyx. What will be Vyx? Charge divided by 2 pi epsilon, charge on conductor Y ln d2 divided by d1. So at the place of 2 we have x here. So distance of conductor X from Y divided by dy. So Vyx will be, what is Qy? Qy is nothing but minus q divided by 2 pi epsilon ln dx is nothing but distance of conductor x from conductor y. So this distance is nothing but d divided by dy will be the radius of conductor y. Here we will have radius of conductor x. Okay, so what will be vxy? The potential difference due to vxy due to charge on conductor y. Vxy will be minus of vyx, and minus minus, then we will have plus q, and then d divided by ry. So that what will be the total difference? The total potential difference Vxy will be the potential difference due to charge on conductor X plus the potential difference due to charge on conductor Y. So the Vxy total will be addition of these two quantities. This we will have Q divided by 2 epsilon ln d square divided by Rx into Ry. Let us assume that both the conductors have same radius, so here also we will have r square, or then we will have q divided by 2 will come outside the log, so here we will have pi epsilon ln d by r, where d is the distance between the conductors and r is the radius of conductor. So this is the potential difference Vxy. So the Cxy can be written as Q divided by charge on each conductor divided by the potential difference between X and Y, that is Q divided by pi epsilon ln d by r. So Q and Q will be cancelled and we will get pi epsilon divided by ln d by r. So this is the potential difference between X and Y. Now consider, let's say we have two conductors and these are, let's say, supplied by center tap transformer. Okay, this is the first conductor. Okay, here you may have some load. This is another. This is the conductor for returning current. Okay, this total capacitance we have found as pi epsilon divided by ln d by r, and let's say this current was supplied by center tap transformer, or the neutral is, this is grounded. Okay, so we will have equal potential drop between any line and the ground. Let's say the total potential difference here is VE. Here we will have a potential difference V by 2. Actually we are interested in finding out the line to ground capacitance or line to neutral capacitance instead of the capacitance between the lines. Okay, so if voltage is halved, what will be the effect on capacitance? If this voltage is halved here, the capacitance will be doubled. So capacitance between any line and neutral will be 2 pi epsilon divided by ln d by r. Okay, and this whole capacitance can be broken into two parts. If this is C, this will be 2C, and this will also be 2C. 2C in series will give you C capacitance. Also Cyn will be 2 pi epsilon divided by ln by d by r. Okay, so by this derivation I wanted to explain the basic concepts involved in calculation of capacitance. So you have to assume charge on a conductor. Due to that charge, first find out electric field, then the potential difference, and then finally capacitance. As we discussed in case of inductance, the formula for inductance, the per phase inductance was 2 into 10 to the power minus 7 ln GMD divided by GMR. So here also, before discussing further, let me write down the general formula for capacitance. Per phase capacitance, or let's say line A and neutral. The per phase the formula for per phase capacitance in any system, this will be 2 pi epsilon divided by ln GMD divided by GMR. Not for any system. This is for balanced positive sequence charge. Okay, balanced positive sequence charge distribution. This formula will be applicable in case of unequal phase spacing in the voltages in stranded conductors, stranded and bundled conductors. It can be derived with the same concept, but that involves only mathematics apart from the concept that we have already discussed. So I am not doing that. Let's say we have 3-wire system, equally spaced 3-wire system. Distance is d. So GMD will be d into d into d. Okay, if we consider this conductor only, we have only 2 types of distances. So d into d to power 1 by 2, that is d. And what will be GMR? In case of calculation of inductance, this GMR and this GMR are different. Here what we do, this is taken as R dash, while in case of calculation of capacitance, this will be simply radius. Okay, so the capacitance between line A and neutral will be 2 pi epsilon divided by ln d divided by R only. For stranded conductors, okay, in one conductor only there will be 2 or more subconductors. Okay, so in that case, we apply the same formula as the case of single conductor, but we will have to take some approximations. We will have to take the approximation of uniform charge distribution. Uniform charge distribution. If we have, instead of one single conductor, if you have a strand of conductors, the charge distribution are not uniform. They are not exactly uniform as in the case of single conductor, but for the calculation of capacitance of stranded conductor, we assume that we have a uniformly charged distribution. The second assumption is the electric field near the surface of conductor is same as the electric field of solid conductor. Let us assume instead of a stranded conductor, we have a single conductor of radius equal to the outer part of these stranded conductors, and if we had an electric field E here, so on the surface of each stranded conductor we assume that we will have the same electric field. Okay, but this is not the case. Due to charge on other conductor, there will be some distortion in the magnitude of electric field. But for the calculation of capacitance, we assume that this E and here E will be same. Okay, and the third assumption is this is also the same assumption that we take in case of solid conductor also, that the resistivity of the conductor is 0. It is a pure conductor, and if resistivity is 0, the electric field inside the conductor will be 0. Inside the conductor equal to 0, which is possible only in ideal case. If conductor has some resistivity, there will be the electric field inside the conductor, this will not exactly be 0. Okay, so for a standard conductor also we can apply this formula. Let us take an example of a standard conductors. Let's say we have 3-wire system. This is for A, this is for B, and this is for C. This is A dash, B dash, C dash. The distance between the two strands are, this distance is D, radius is R. Distance between A and B phase is, let's say, DAB. Here we have DBC, and phase A and C are, this is DAC. Here we have balanced positive sequence charges, that is QA plus QB plus QC will be equal to 0. But due to unequal phase spacing, the phase spacing is not equal. Due to unequal phase spacing, unbalanced positive sequence voltage, or we can say due to unequal phase spacing, balanced positive sequence voltages are not obtained. So line to neutral voltages will be different, hence giving unequal phase to neutral capacitances. But this can be avoided using the transposition of the line. The transposition I have talked about while in case of calculation of inductance. But the balance can be achieved by transposition of the line, that is interchanging the position of the conductor A, B and C for equal 1/3 of the lines, 1/3 of the length of the line. So in this case, if we choose transposition, the same formula can be applied, and if we will have transposition, we will have 3 distances. Okay, the distance between position 1 and 2, 2 and 3, and 1 and 3. So GMD will be D12, D23, D31 to power 1/3. And GMR will be, what will be GMR? For this conductor we have two distances. First is its radius only, and the second distance is d. Similarly, for second conductor, its radius into d. So we have four distances. So either we can do r into d into d to power 1 by 4, or simply we can say r into d to power 1 by 2 into r into d to power 1 by 2, then again multiply these two quantity and power 1 by 2. So overall you will get GMR as r into d. In case of calculation of inductance, at the place of r we have to take r dash. And in one case, let's say in place of two conductors we have three conductors. In A phase only, let's say we have three conductors. So what will be GMR here? Let's say distance between each conductor is d and its radius are r. So for first conductor there will be three distances, r, this d and d to power 1 by 3. Okay, and same will be for second and third conductor. Okay, so overall how many different type of distances we have? R, D and D. So we will multiply three distances, because the same three distances are applicable for second and third conductors. So overall we have three type of distances here only. So the overall GMR will be R into D square to power 1 by 3. Similarly for conductor of 4 strand, this will be R into D cube to power 1 by 4.